Then is the YouTube, it's already online, so whenever you want, you can start.
Okay. Let's start. Empecemos. Hola a todos, muchas gracias por su asistencia, por estar aquí. Hoy tenemos una invitada especial, tenemos a Audrey Corbeil T. No sé, I'm sorry if I pronounce it wrong. Em, ella es profesora del Departamento de Ingeniería Electrónica y Computación de la Universidad de Sherbrooke en Quebec, Canadá. Y muy amablemente nos ha eh, aceptado la invitación para dar una conferencia. Ella lo va a hacer en inglés, por lo que les pido a todas las personas que están en Zoom que activen la parte de captions, de subtítulos en su Zoom para que puedan seguir la charla más fácilmente. Como decía, Audrey trabaja en Canadá, es parte del IEEE, de la Sociedad de Nuclear and Plasma Society. Ha trabajado también en el CERN y tiene mucha experiencia sobre este tema que nos va a conversar, que es justamente la forma de hacer análisis de datos, de grande cantidad de datos en detectores de radiación y de partículas. Sin más, le dejo la palabra a Audrey. Audrey, thank you very much again for your collaboration with us, with our seminar. You can start wherever you want, when you like.
All right, thank you very much for the warm welcome, and welcome to everybody. It is my privilege here today to talk about a little bit of instrumentation in radiation, and especially my research, which consists of high velocity detectors, so detectors that create a lot of data, and how we can deal with that. Before I get into the interesting part of the presentation, I do have a few housekeeping bits. So this lecture is given as part of the IEEE Nuclear and Plasma Sciences Society Distinguished Lecture Program. So this is a program which lets you invite experts from different fields in NPSS. Whether you're a chapter, section, college, or university, you can invite people to come lecture. And so we also encourage you to become an IEEE member. For students, it is a very low rate. And I would also like to point out that there is IEEE educational videos from these same experts on topics ranging from DAC systems to detectors to all sorts of other subjects. So that is an excellent resource. The society I am part of also has several NPSS journals, conference records. If you're an IEEE member, you get discounts for our conferences and all sorts of other benefits. I invite you to go on the website to see all the benefits you could get as an IEEE member. And these are the conferences that we sponsor in our society. So we have several over the year. Depending on your focus, you might be interested in one or more of these ones to present your work. Our biggest one is the Nuclear Science Symposium, Medical Imaging Conference, and Room Temperature Semiconductor Detectors, which has about 1,200 to 2,000 attendees. And so you can look up the other conferences to see if those are a good match for your research. Finally, the different publications that we have. So we have several different journals. If you are an IEEE member, you have access to these journals for free. Well, for the rate of your registration. All right, so this is the housekeeping for IEEE. A little bit about myself. So I come from electrical engineering. So I'm not a physicist. I do not understand all of the physics, but I understand enough to be able to work in this part of the field. I did my postdoc at SLAC in California. So I got to see one of the largest particle accelerators in the world, and I got to see the largest one as well. I worked 4 months at CERN at the Large Hadron Collider. I'm currently an assistant professor at the Université de Sherbrooke in Quebec. And yes, it is a French university. My native language is French. My expertise is in embedded machine learning. and I'm also an IEEE Women in Engineering Liaison. So for all of the women in the field, and as well as all of the other diversity, welcome, and I hope that you stay with us. And finally, I am a Canada Research Chair in Real-Time Intelligence Embedded for High-Speed Sensors. So that is just one of the credentials that I managed to obtain in Canada. But where is this Université de Sherbrooke? So if you look in the northeast of the American continent, so close to the edge between, so this is the US and this is Canada. So we are right on the edge near Montreal, for those who know where Montreal is. So this is a rather recent university, founded in 1954, but it is a relatively big university with 40,000 students, 3 campuses. And we have been increasing our research funds a lot in the last few years, and our research has grown a lot. The laboratory where I work is called 3IT, and this is where we have common labs. So instead of having every researcher build their own labs, in our university we have a common lab, especially for microelectronics and electronics, as well as some mechanics and photonics. So all of these labs are shared, which reduces greatly the cost of both the lab space, the infrastructure, and the human resources. So we also share lab technicians. So we are now 1,100 members working in this building, all working in parallel and together in synergy to get this research going. My group personally is currently 8 students, but in total, we have a larger group of 50 students in this research building with 500 other students. So it is a big community, and that is very, very helpful. Another note, we used to have 2,000 square meters of labs, and we just finished an expansion that doubled this surface. So it is growing very rapidly. So this is a little bit about where I come from and where we study. And now the reason why you're here, let's get into the meat of the subject. So we'll start by going over what the problem is with new detectors. And I'll be showing a few of high velocity applications that I'm working on and explain why machine learning is a solution that we're looking into and what hardware we'll need for that. I'll give an application example from start to finish, which is the cookie box. I'll explain what the cookie box is in time, and I'll finish going over the challenges of using machine learning for science. So the problem with new detectors, it boils down to growing pains. So some things are growing faster than others, and that is causing us some issues. To start with, we have the detector chain. So how does a detector go from a particle or a physical measurement to digital information, a bit? So we start with a particle that will go through a detector and become an analog signal. So a electrical signal usually, though it could be other forms, but in this case, we'll stick to only electrical signals. The information can be encoded in the amplitude or the current or the frequency. There are different ways to encode the information in the signal. And then this is digitized. So it's turned into ones and zeros. And finally, it's turned into a file. So these are different steps that are taken before we have the actual data set that you will encounter when you take a data set from an experiment. So the detector is what will transform the particle into an electrical signal. And then we have the data acquisition system, which turns this analog signal all the way into a data stream of bits, so a sequence of bits. And then the online analysis nodes, these are usually servers or computers that will actually transform the data stream into files that are organized. And finally, the files are saved to disk. So these are the steps that I'll be referring to throughout this presentation when I talk about the data, the detector chain. So how we go from a particle to a digital information. I'd be particularly interested in the DAC part, so the data acquisition system that goes from the detector to the online analysis nodes. But to understand what is going on and what we need to do in the DAC, we need to understand what's going on with the detector. So how does the detector manipulate the information that is coming in the particle, and how is it representing that information so that we can differentiate the data from the information and only keep what's really important and what we're looking for. So in the last few years, in fact, in the last few decades, we've been improving our detectors. So the new generation of detectors have way more pixels. So if any of you have followed the sequence of cell phone cameras, for example, cell phone cameras, the very first cameras were very, very low pixel, and the most recent ones have millions and millions of pixels on them. So we have more pixels, and every pixel is a source of data. We also have faster sampling rates. Again, with the video, we went from 24 frames per second, and now we're usually having 60 frames per second, and some places have 120 frames per second. The same thing is happening in science at much, much higher rates. So some of the experiments that were running at 120 events per second are now running at 1 million events per second or 40 million events per second. So we have to collect all this data that is happening very, very fast. So we have more events that are happening for every unit of time. We also have better sensitivity and dynamic range, which means we're better able to see the very, very tiny signals. However, to be able to see the tiny signals and the big signals at the same time, we need to have this very wide dynamic range, and we need more bits per unit to be able to represent that full range. And finally, we have some detectors that have much, much larger surface areas. I'll be presenting a few of them, but we're moving from things that have a few centimeter squares of sensitive area to meter squares and hundreds of meter squares of sensitive area. So all of this combined together results in multiplications upon multiplications of data. So we have too much data for the acquisition systems who have not grown at the same rate. So we have this tsunami of data that is happening for several of the new detectors and several of the new experiments that are happening. So if we were to collect all that raw data, if we were to try it, it requires a lot more wires. And to transmit on each of these wires, we need more power. And in some cases, we're talking kilowatts to megawatts of power for just transmission. We're not talking about powering the detector, just for transmitting the data. So this is becoming a huge issue in how much power we're consuming. And as we all know, we are facing an energy crisis in that we have, the more energy we create, that's bad for the environment. So we do want to reduce our energy consumption. And so data transmission using megawatts is not a good plan. We also require very sophisticated short-term storage. So parallel SSD arrays that are very powerful, and we need some redundancy to protect the data. And these become very expensive. Every single block of data that we save, it generates costs for long-term storage. So we do need to put the data somewhere, and it has to be in a facility that is protected. We need to have some server access to be able to go get that data. And every time we transfer that data somewhere else, it also uses power and costs something. So we're talking millions of dollars, millions of US dollars per month to maintain those facilities. So we have to take into account when we save data, is that data necessary to be saved? And it also adds to transfer times and compute times. So the larger data set we have, the longer it takes to transfer it and the longer it takes to analyze it. And that is human hours that are used for that. So we have to have somebody who takes care of starting and stopping the transfers and building the computation. And if you're anything like in my group, the analysis test never works on the first time. So you have to do it 2-3 times. So if you do it on a big data set, that's some compute power that is in some ways wasted. So we want to reduce the amount of data that we are actually going to store. So collecting all raw data works for some of the experiments that generate less data, but there's a pivot point where it becomes too much data. Now, the leader in data generation is the Large Hadron Collider. They have been generating immense amounts of data since it's been built. And this is not going to stop. So as of 2018, so this is a little dated, but I haven't found the more recent numbers yet. So as of 2018, it was generating 200 gigabytes per second. This is after the level 1 triggers. So there's hardware triggers in the middle. So this is just the data that comes out of the detectors. There's more data that's already been erased inside the detector. And to be able to handle that amount of data, they need 2,000 compute nodes. So and I have seen this, they have a supercomputer in the room next door to the detectors. This is true for both CMS and Atlas, the two large detectors. So both of them have racks of computer next to the detector. And all of this to save about 2.5 gigabytes per second at the end. So there's about 2 orders of magnitude compression happening in those compute nodes. Now they're doing an upgrade right now, and they're finishing it up. And the next upgrade is going to be the high luminosity upgrade. And the high luminosity upgrade, they're estimating that will be 5.5 terabytes per second that will be generated outside the detector. And if we scale the 2,000 computer nodes and we use the same technique, we would go up to about 30,000 computer nodes, which is a ridiculous amount of computers, and that's not what they're planning to do. So they estimate that they will need about 3,000 nodes, but they will need to have GPU coprocessors on those nodes to be able to handle the data. So the latest plan that I found is that they will use CPU, GPU nodes, about 3,000 of them, and this is for 2029. So they're still working on exactly how many nodes they will need, and they're targeting about a 61 gigabytes per second save rate at the end of the entire compression. So again, now we're talking about more 3 orders of magnitude compression from the exit of the detector to the save point. We're also talking about a future circular collider. So this is several decades in the future, but they're already starting to see what they will need to build such a large endeavor. And this, if we use the same data systems that we have currently, the same detectors, but we scale them up to be able to deal with these energies, they expect to have about 2,000 terabytes per second, which is a huge amount of data. And just to transfer that data is about 2 megawatts. So they're not at the point yet of seeing how they're going to analyze and compress this data. But if they were just to transfer it using the current transceivers, that's 2 megawatts of power just to transfer data to the compute nodes. So this is becoming a very large amount of power. So we need to have other systems. Now, I mentioned that LHC is the one generating the most data, and it has been generating the most data for the longest time. But as detectors have improved and other instruments have emerged, other facilities are also starting to encounter the same problems. One of them is the LINAC coherent light source at the SLAC National Accelerator Laboratory. And this is a giant X-ray laser. So where they're using the accelerator to accelerate electrons, and you send those electrons in what we call an undulator, and it makes the electrons dance back and forth. And there's a physical process called Bremsstrahlung, which means that there will be emission of photons in the direction that the electrons are moving forward in. And because they're all moving forward together, the light becomes coherent, which makes it a laser in X-ray energies. So we now have an X-ray laser which can take images of molecules. So some of the images of the COVID-19 virus we're taking at this facility. So the coherent light source 2 will be going at 1 million images per second, which means that each of the experiments will be generating 20 to 1,200 gigabytes per second. So that's like around 1 terabyte per second for some of these. So the current data acquisition systems can't quite keep up. Just to show, if we were to be able to design something that could keep up, if we assume 1 terabyte per second to keep our numbers simple, and we take data for 12 hours, which is actually, so if we have a perfect shift, we are able to take data for 12 hours. The experiments in this system last for 12 hours. So assuming we have a perfect shift, we get 43,200 terabytes every shift, which is the equivalent of 56 years of 4K movies. So that's a lot of data in 12 hours. And that data is not analyzed. That data is just raw on a disk, well, several disks, to bring back home and try to analyze. And this means that to store that data is 1.3 million US dollars of storage costs created every shift. Now, like I said, we rarely take a full 12 hours, but that's like the extreme case, and it's a not negligible cost to do this. So these are the facilities. There's several other ones. I'm not going to go through all of them, but I do want to present a few other high velocity applications that are research projects that I am working on with larger groups. So one of them is at the LCLS2 at SLAC, which is the cookie box angular streaking detector, which generates about 168 gigabytes per second of data. However, we want to use it for a low latency diagnostic detector. So we need to do the analysis in as few microseconds as possible. And we'll be coming back to this one because this is the case that I will show from start to beginning how we designed this data acquisition system. But other interesting projects that we are working on is a 1 billion pixel camera for X-ray applications. So this is not medical X-rays. This is for X-rays used in particle physics to image matter. And these are equivalent to about 2 gigabytes per image. And we plan to use them at about 1 to 100 kilohertz. So 1 to 100,000 images per second, which, if you do the multiplication, also falls into terabyte per second range. And considering the density of pixels, we need some strategies to get that data out. I'm also working on a liquid argon detector for dark matter search. DarkSide 20K is currently being built. I'm working on the next one, which is called Argo. And Argo will have 200 square meters of detectors with millimeter granularity, and we'll have about 20 million detections per second. This isn't so much the amount of data that will come out, but the how wide it is. So we have 200 square meters that we need to collect into one point to be able to do the analysis. So there's a very interesting challenge there too. And finally, medical imaging. So we are working at Sherbrooke to develop the very first time-of-flight computed tomography scanner. So computed tomography, the common CT scan that we hear in hospitals. So it's basically X-rays that are used to create a 3D image reconstruction of tissues inside the body. Currently, the techniques they use require a little more radiation that we would like, and we're hoping to reduce the radiation dose necessary by computing the time of flight of every single X-ray photon. And if we have the time of every single X-ray photon, the data multiplies, and we end up with about 120 terabytes per second for a square 14-inch by 14-inch X-ray radiography plaque, which is our starting point. So we can't get that data out. There's physically not enough space for cables. So we need to actually do the computing inside, and we're working on that currently, and it's moving forward pretty well. So in all these cases, collecting the raw data is impossible or too expensive. So how do we get this information? Well, we want to analyze, reconstruct, and compress the data inside the DAQ, inside the data acquisition system. But most of the current algorithms to analyze, to reconstruct, or compress are actually iterative. algorithms, which means it's algorithms that you do forward and then you check backwards and then you start again. So you have to loop the algorithm 50 to 500 times to be able to finish your reconstruction or to finish your analysis. So for very complex data, our iterative algorithms, they're not good for real-time applications, right? We can't put them inside the data acquisition system because we can't have something wait in that time. Everything has to flow and stream through it. So the question is, can we replace the current algorithms, which are iterative, by something that is more computationally efficient? And that's where my research comes in, which is focused on edge machine learning. So we go back to our detector chain here, and we are going to replace the data acquisition system here by a system based on edge machine learning. Right, so we're going to use we're going to use machine learning algorithms, and we're going to put them inside the data acquisition system so that they can do the analysis, they can do the compression in real time with very limited computation resources. So remember, this is physically on the same card as the detector. We're very near it. It is not a full computer. So we are constrained in space, we are constrained in power, we are constrained in heat dissipation. All of these things need to be controlled. So we are very limited in what we can put there, but we do have some opportunities. The other advantage is because we're doing some smart analysis, we can also give back information to the detector. So we can control if the detector is being more sensitive or less sensitive. So we can adjust some of the parameters of the detector. And in the same way, we can adjust some parameters of the source to say, hey, your energy has been drifting. Your energy is lower than it should be, or something's wrong. So we can raise some alarms here that is interesting. And we can also give extra information to our online analysis nodes to tell them the event I just sent you is this type. And then they can bend them and do the analysis differently for certain events compared to others. Now, this is not necessarily new information, but it's something that we can actually augment compared to what traditional algorithms were capable of. But why machine learning? Why would we want to use something so new and so black box? So there's this perception that machine learning is a black box and it's a little random. It is not. There is something to be understood in it, but we want to better understand what it actually is and why it's such a good candidate for an edge application. So what machine learning is different from traditional programming. In traditional programming, you have your input data and you build a program that will give you an output. When we do machine learning, we're going to give the input data, we're going to give the output data that we want, and the program will build itself. So what determines the quality of the program or the quality of the algorithm is actually the quality of your input and output relationship. So if your data set is not good, then your program will not be good. If your data set is limited, then your program is limited. So when you think about machine learning, how good it is or bad it is depends a lot on what you used to train it. There are different structures. I don't want to give a class on machine learning. There are people on the internet that are much better than I at teaching what machine learning is and how to use it. But I will quickly go over. We have nodes that are connected to other nodes. And in that process of computation, there are multiplications, additions, and an activation function, right? And you have fully connected, which are the very first neural networks that were made, where every single node is connected to every single node in the next layer. You have the convolutional neural networks, which actually have a filter that goes around the image or the 2D, 3D, 4D representation of information, and we'll find relationships in proximity. And you have the recurrent neural network, which is excellent for time series, like natural language. So they will actually remember the previous input and deal with that. So those are the three basic ones, and then you have a lot of different variations on those three. I don't want to go all in all the structures, but I will show one, which is the autoencoder. So the autoencoder is particularly interesting for our applications because it has this compressed center over here. So the way an autoencoder works is that you have your input and your output, which match exactly. And what the network is trying to learn, it's trying to learn a compressed representation in the middle. And once you finish training it, you can just split it in the middle, and you have a encoder, which compresses information, and a decoder, which decompresses it. So this is one of our architectures that we work a lot with. As I said, a lot more to see in machine learning. That's not where I want to focus today, but if you're interested, I encourage you to go look up the various courses that exist on the internet. But why we want machine learning? Well, machine learning is very good at recognizing patterns, which also makes it very good at recognizing anomalies. And in detectors, a lot of the things that we're looking for are patterns or anomalies, things that we're trying to find in the image or that aren't supposed to be in the image but are there. And it's very good at nonlinear regression, which means it's good at reconstructing the path of particles in the different detectors. So these are three applications that it's very good at. And it's faster and more flexible programming. So it's actually shorter for a very complex problem to train a machine learning system than to try and code it manually. Now, there are cases where it's easier to code it manually, but in some of the cases where we don't know the relationship between the input and the output, it's much faster to have the computer find it for us. It also has a lower computational burden. And here, what I mean is compared to the iterative reconstruction algorithms, for example, a machine learning will use less operations. Okay. There are machine learning systems that use way more operations than they should. That is something we can definitely discuss in the question period. But generally, machine learning has a lower computational burden, and that computational burden is made up almost exclusively of multiplications and additions, which is something that hardware is very good at. So that means that by going down to hardware, we get very fast inferences, and so we can make low latency decisions. So we can have the result very quickly so that we can react to it very quickly. So to do that, we're going down to hardware. When we speak about hardware, the one most common is the CPU, so the computing unit in most computers, most phones. And this is very flexible, but only does one computation at a time. Of course, if you have several cores, you can have several threads happening at the same time, but mostly a CPU does one computation at a time. The GPU, so the graphics processing unit, is actually a very, very good matrix multiplier. It's made up of thousands of arithmetic logic units. So 1,000 of little units that are excellent at multiplication, they are excellent at addition, and they are all working in parallel. So you load all your data and everybody computes at the same time. And so you have the computation much faster because you're working in parallel. However, it is batch oriented, which means to take full advantage of a GPU, you need to be able to batch your data into large enough chunks. And loading it into memory and pulling it out of memory actually takes a pretty long time. So, but you say, we use it for gaming, so it can't take that much time, right? You don't see that latency. Well, it's actually in the millisecond range, and our human brains aren't quite good enough to see milliseconds, right? That we start seeing delays at about tens of milliseconds. But when we go in particle physics, we're going to start seeing events that are happening in microseconds, things that are happening in picoseconds, right? So we're not talking about the same range. So when we talk about GPUs, they're a little bit too slow because of the memory transfers. And so they also need a host CPU. I will note that a lot of the new GPUs actually work on their own for exactly this type of application. So some of them don't need a CPU anymore. They use a lot of power. So they're hundreds of watts to a few kilowatts, depending on the size of your GPU. And of course, they take up a lot of space and they heat up a lot. So you don't want to take something that is very power hungry and will generate a lot of heat and put it next to your heat sensitive detectors, which will create more noise because they're too hot. So GPUs definitely have their place, but their place is not at the edge. What is interesting to put at the edge is the FPGA. So this is the Field Programmable Gate Array. It is a series of gates. So basically logic gates, the AND, the OR, the XOR, that is set into a matrix, and you can reconnect them however you want. So it is highly configurable, it is very efficient, and it has a very high I/O capacity, especially when you go into the ultra scale level. And this is actually the type of circuits that are used in communications. So in the cell phone towers, they have ultra scale FPGAs to be able to take the input outputs of all the cell phone calls. It's easily programmable, but learning to program one is hard. So it's a different paradigm of programming. And so to become an FPGA expert is a completely different thought process than becoming a C++ programmer, for example. FPGAs, because they have a reprogrammable wiring, have a limited clock, right? So the frequency at which they can work is lower. So for example, 100 to 200 megahertz is the clock for FPGAs generally. Some of them can push to 250, 300 megahertz. But in comparison, a CPU or a GPU will run more towards the high megahertz, low gigahertz range. So it's a little slower for that. And you're, of course, limited by what fits on the chip. So you can get a bigger one, but at some point, they don't make any bigger ones. So there is a limitation there, but the limit is pretty high. But why would this work for a neural network? Well, here I have a fully connected neural network. And imagine that this is programmed on the FPGA. So every single little node here is a little unit that is very good at multiplying and adding. And it has its function. So every single one of these is a little neuron. And I can make as many of those as I want on the FPGA. And I can connect them however I want. So that means that I can load into my database buffer one event that I want to do an inference on. And then this one can go in the first layer. And while it's in the first layer, the second event can already come in. And then the first one finishes computing the first layer and goes into the second layer, which means the first layer is now free. And we can move the second layer. And again, with the third event, as the first event is in the third layer. So now I have 3 events computing at the same time. And I can have a fourth one, and everything is computing at the same time to get my classification, for example. So that means every single neuron in a layer is computing in parallel, and every single layer is computing in a pipeline. And that maximizes the throughput I can get. And this is something that I can do in an FPGA that I cannot do in a GPU. So that's one of the advantages of the FPGA over the GPU, to be able to do this pipelining at the same time as the parallel. In the GPU, I will need to wait for one to finish the one layer and then reload the new values to do the second layer. Finally, there's the ASIC, which is a custom chip. So the custom chip, you can make almost anything you want for them in computation. It's extremely efficient because you only make the circuits that you need. You make the custom I/O, so the input and outputs that you need. There's currently very interesting research and developments made in 3D. So you have several layers of silicon on top of each other. And the plan eventually is to have a silicon layer that is the detectors, and then a silicon layer that is the analog processing, and then a third layer that is the digital processing. So you have the entire chain in silicon. So that is, we're not quite there yet, but that is something that is currently being studied. You can make parts of it reconfigurable in software. You can literally put FPGA fabric onto an ASIC. However, it is extremely expensive, and the design cycle is very long, from 2 to 5 years easily. So this is something that is usually only done when there is no other solution, or we know that it is the kind of chip that will be reused for several applications to come. So finally, well, now that we have all this information, let's go do the proof of concept, right? Let's see how all of this comes together to actually make an edge machine learning data acquisition system. So this is a cookie box. This is a detector that is used with the X-ray laser. So the X-ray laser goes right here in the center, and there is a very low pressure neon gas. Right? And so when the laser comes through, the energy is high enough that it can kick the electrons off the atoms. And these detectors around it will collect these electrons. And from these electrons, we can sample and see the shape of the pulse that came through. Right? So we have a pulse that goes through, and we want to see if the shape is what we are expecting for our experiment. And to see the shape, we have to see the shape in time. So to be able to see the shape in time, we add an electric field that turns very quickly. And because it turns so quickly, we can get attosecond resolution in the time domain of this detector. So it can tell us in the pulse, in time, if we had any spikes, or if we had one single spike. I will illustrate it a little later if it's not quite clear yet. So this gives us this kind of image where we have, these are our 16 detectors around. These are the 16 channels. And for every channel, they have different energies, right? And because there was this electric field that was turning very fast, some of the events were kicked at higher energy, and some were kicked at lower energy relative to one another, which means in this case, we are able to see that there were 2 subspikes in our pulse. So the pulse shape had 2 spikes in it instead of having one neat pulse. And that is something that happens because of the process of creation of this X-ray laser. The pulses aren't always clean. The pulses aren't always there. Sometimes they just don't even generate. So we want to be able to identify the ones that we can use for the experiment and the ones that we can't use for the experiment. So the cookie box is in here, in front of the experimental hutch. This is where all the other instruments for the experiment are. And we want to know before we save the data if the pulse has the correct number of subspikes for the experiment we're currently doing. So we can have sometimes 4 subspikes. This is not used for experiments. 2 subspikes is often used. So we can actually see something interesting with 2 subspikes. 3, it depends on their exact shape. So we're curious to see, and we want to rebuild this. Ideally, we want 1 for most experiments. So the idea is before we save the data, we want to know if it's good. So we are going to analyze the data from the cookie box, and this will tell us in the data buffers from the experimental hutch, which one are we keeping? So we got a good one, we're going to keep that one. We got a bad one, we're going to delete that one. So before it even goes to disk, we can tell which ones are good and which ones are bad. So this is the final purpose. This is the purpose of our cookie box. This is how we're going to use it. But how can we do that? The cookie box signals has 16 channels, and each of those channels gives us spikes when it's hit by electrons. And these spikes are turned into this 3D histogram, so in colors and in the channel dimension and the energy dimension, to be able to identify the spikes. Now, turning this into spikes, the current method, so the method they were using up until a few years ago, is to do the full reconstruction, which is an iterative process, which takes a few seconds for every event. But we want to be able to do this in less than a microsecond. Why less than a microsecond? Because the LCLS2 will be running at 1 million pulses per second. And ideally, we want to have the answer before the next one. So we need to be able to take the analog output, turn it into this histogram. So this is all some signal processing, digital signal processing. Put it into the histogram, and to do the reconstruction of the pulse, but in this case, we're not doing the full reconstruction. We're just going to count the number of spikes using machine learning and to obtain the number of subspikes and do all of this in less than a microsecond. So the first thing we did is train the neural net that is going to do this transformation to see if it was possible from this to get the number of subspikes. So what you're seeing here is what we call a confusion matrix. The confusion matrix has the ground truth on this axis. So this is the truth. And this is what my neural net predicted. And if my neural net is perfect, I get 100% on the diagonal. As you can see, our neural net is not quite perfect. We're very good at saying when there's no pulse, no spike. And then we're a little less performant when we have 3 subspikes. But we can also see where the confusion is. So we can see that we're mixing up the 2 subspikes and the 3 subspikes. But generally, this is a pretty good analysis, right? It's actually pretty good than to the previous method. For those that are interested, here is the model parameters, but I don't want to extend too far into that because of time constraints. So this is where we need to fit our items. So we have our detector, and here we have the ADC that turns it into digital bits, and we have FPGAs, and then the big FPGA that's going to hold our inference engine, the neural network, is going to be here. So we're going to do the pre-processing on these and the inference engine on these, which means all our code must fit into these FPGAs. But how do we turn our code into something that works on FPGAs? We have HLS for ML, which is an international consortium that is working on this open source tool that turns neural networks into HLS, so high-level synthesis language. And then you can turn high-level synthesis language into FPGA bit streams, so you can program your FPGA. There's a few extra steps involved. It's still under construction, but it is doing quite well. So when we first do our HLS for ML, remember, our #1 criteria is that we want to be under 1 microsecond. When we ran it in HLS for ML, we ended up with 2.8 microseconds. That's no good. We want to be under 1. So my student did a lot of optimization work on the code that was produced by HLS for ML and managed to optimize it down to 0.2 microseconds. So 0.2 microseconds is under 1 microsecond. So we went and tested it in the lab. We don't have access to LCLS2 just like that. It is a big system. There's a long process to get access to it. So we actually emulated the behavior of the cookie box using this device, which is an arbitrary waveform generator. which send the signal down to the digitizers that we have here, and the FPGA, which is right under it. And then the data from the FPGA goes to the computer, and this is an oscilloscope to monitor, and this is the power source. So we have the AWG, waveform generator, digitizers, and the FPGA. And this is what we measure. So the yellow line is the AWG markers. So this is when the AWG says, I'm starting to send data. And the green pulse you see here is the machine learning block output. This is the FPGA saying, I have the result. So the time between the AWG starting to send the data and the machine learning block saying, I have finished doing the computations is 1.4 microseconds. But remember, I said there was 1 million pulses per second, 1 million pulses per second. So every single pulse, we take data for 1 microsecond. So if the pulse width is 1 microsecond, the FPGA only gets its data, the complete data, after 1 microsecond. So the time it takes for the computation is actually 0.4 microsecond latency, which includes from the point that the data is generated, it includes the ADCs, it includes the transmission towards the FPGA, and all the data preprocessing, and all of the block inference. And all of that happens in 0.4 microseconds, so in plenty of time before the next pulse. So we've managed to make the end-to-end emulation. The neural network accuracy is actually around 90% on the tests we made on the FPGA itself. One of the reasons that it's so good is that there is no noise, and it was done on a subset. So we are furthering the tests for long-term performance. We're actually under our 10-watt target. We're at 5 watts, which is very low power, and our latency under a microsecond. So we've managed to prove from beginning to start that using machine learning on FPGAs is a viable route for high data streams. So what have we learned? We've learned that one of the biggest challenges that we're facing is being able to optimize the performance. So if we want very high confidence and very high accuracy, it's going to require very complicated neural networks. But very complicated neural networks means that the size and the latency on the FPGA is going to be much bigger. So that's going to mean that we're going to need more power, we need more time. So we need to balance these from one to the other. And it's very dependent from case to case which one we're going to try and favor. That's one of the challenges for the whole design. And what you're seeing there is the final design, but there have been over 24 different designs over 2 years to get to this final design. I've mentioned before, the quality of your algorithm is only as good as your data set, and training data sets in particle physics they are very hard to come by. What I mean by that is in your data set, you can either go the simulation route. Simulation route means you need to have a model that is validated, right? So you have to make sure your data is representative of the real data that you will get eventually. You have to be careful not to introduce any bias, right? So sometimes you're going to get a data set that is focused on a small area of types of particles, and then once you get in the real world, suddenly there's all these other particles and noise sources that you didn't account for. On the other hand, if you take a measured data set, then you need to actually label it. And to label it, you sort of have to trust that the algorithms that we've always been using are actually trustworthy, which some of them haven't always been verified. So, and some of them don't have 100% accuracy. So you're training using labels that may not be 100% accurate. You may end up having anomalies in that data set. And if you don't remove those, then you're training to learn anomalies, or you're training to learn to ignore anomalies. And always matching the formats, always a huge challenge when you get real data sets. One of the other challenges, which is more on the human side, is how do we convince the users that the machine learning will give them accurate information? I mentioned at the beginning, there is this perception that machine learning is black box and that machine learning is random. It is not, but it is hard to explain. So having these systems for validating the results for all the types of data that will go in, how to interpret it, can we measure the uncertainty on the computation that it does? And every single science application should use raw data sampling to be able to compare and validate that the algorithm is doing what we expect it to. And finally, the data and model provenance. So here's the case. We have a data set. We use it to train different models. And these models, in turn, will generate data sets that have some results. But then when somebody else comes and trains the fourth model, they realize that there is a bias or a mistake or some anomalies in the data set. How do we transmit the information that the other models may have the same bias baked into them? And I have a very real case that is coming up. So when we talk about generative AI, which the most famous example is ChatGPT, right? So ChatGPT-2 and ChatGPT-3, they were trained on data that was pulled from the internet. And now the internet is full of data that was generated by ChatGPT. So the next generation of ChatGPT will train on data created by ChatGPT. So how do we manage that? And I do not have an answer. That is something that is very interesting to follow, because now we're having recurrent training. I don't know how to call that, but the point is following where the data is coming from. Has it been modified? Has it been modified? Where are the biases? It's very difficult. It's a very interesting challenge. So what I want you to remember, because there was a lot of information here, edge machine learning is one of the keys we have to exploit very, very high density and high velocity detectors that generate a lot of data. It's also one of the solutions for very low power low power analysis on the edge. And all of this will help us a lot with science, so we'll accelerate critical discoveries. But this is still a very, very new field, and there's a lot of work to do to develop the tools, the methods, and how to best use them. So thank you very much for your attention. And of course, you can ask me questions. And if you prefer, you can also email me. Thank you very much. I hope I'm still on time.
Thank you very much, Audrey. It's very interesting, your talk. And open for questions. If anyone have a question, please. Luis, I know you have a question. Please.
Thanks a lot for your talk. And as Denny said at the beginning of the seminar, we share with Denny and another colleagues we are working in a cooperation which is called LAGO, and I will share screen to illustrate what we are.
I'm sorry, do you want to share something on your screen?
Yeah, I will. Let me first select what I'm going to share, and then I will share to avoid any confusion.
But you can give me a minute because I have a problem with my browser, so
I cannot share.
No, you're sharing, but you're sharing some
yeah, you can.
document confident, super confident.
No, Latin American Giant Observatory. No.
No.
Come on. Okay. our collaboration is very distributed. Goes from Mexico to the Antarctica, and we have several detectors. The blue cans that you see here are the detectors. And,
Luis, perdón, no estás convirtiendo en serio, estás convirtiendo en un documento de alguna acta, alguna cosa.
¿Sí? ¿Por qué?
Sí, sí.
Ya no está.
Now say.
Okay, no.
It's what I was saying, that we have these detectors from Madrid to Antarctica, from Mexico. And these detectors are on field. I mean, in the Antarctica is a real place where they are, and in the Riobamba, here are some pictures. This is Dennis, okay, and this is the extreme instrumentation sites. This is in Ecuador, Chimborazo, and this is in the Antarctica. And the point is that we are implementing what you have just mentioned is an edge computing infrastructure. That means that you will have at the field level some sort of computation. Then at the institutional level, the data will be processed at this level and then consolidated with the different sites. We will take this all this data to the cloud, no? And then we share the data and see different physics that we have, like all these instruments are affected by the geomagnetic field. Then we have to see if the geomagnetic field is affecting and whatever. I mean, can you say something about this paradigm of edge computing? Because you mentioned that you want to substitute the FPGA or one of the DAQ for these machine learning devices or the machine learning algorithm.
Yep.
Can you say something about this paradigm of edge computing?
Absolutely.
What is your opinion about this facility that we are right now trying to implement?
So yeah, I have several things to say. So first of all, just for definitions, so edge takes a different definition depending on who you ask. So if I look at this, the edge nodes are actually the edge of the, I would say, the backbone internet structure. When I talk about the edge for instrumentation, it's right next to the detector, which is slightly different. It's okay to use them both, just to clarify. So for me, when I talk about the edge, it's really at the field level, right? So where the edge is in the field.
No, I agree. I agree.
Okay. And so the idea is that the more you do locally, the less power you use and the less storage you use. And also there's some privacy issues for some cases, not for this one, but that are interesting because the cloud is just someone else's computer.
Absolutely.
So the more you keep locally, and this is one of the things for cell phones that is very interesting. If you can do the edge compute inside the cell phone, then the data doesn't have to transit by somebody else's computer. So definitely edge computing is something that is gathering more and more interest because we are once again reaching the limits of what we can transfer on our radio waves. And in terms of power, transmitting radio waves is actually requiring quite a bit of computation. And there's a huge environmental problem with data centers, right? Data centers, they don't even want to say how much power and water they're using. So moving things to the edge and making them efficient is something very good for the environment because we still need that data. And so if we do need that data, if we do need that information, then let's get it. But let's get it in the most efficient way possible. Last thing, edge computing for me, edge machine learning is one of the subsets of edge computing. So edge computing uses all the techniques. In our case, because we have these algorithms that just can't be copied onto our FPGAs, right? So an iterative reconstruction using Fourier analysis and quaternions and all these really complex math, we can't put that on FPGA. It's very complicated. So machine learning is a way to simplify those algorithms for specific data sets. In this case, since I don't know what your data looks like, but is machine learning the appropriate or not? I don't know. I don't know what your needs are. But edge computing, definitely. The more you can put on the edge at the field, so on the field level, the less it will cost you at the institutional level for storage and on the cloud level for storage and transmission.
Okay. Thanks a lot for reinforce my idea. The other thing that I wanted to ask, what is your opinion about this tiny machine learning language that is also popular right now? I mean,
Yep.
is having popularity.
It's funny that you should ask that. I just had a summer intern look into it. So I had a summer intern say, hey, go take our application. So he took the cookie box application again, because that's our test case, right? We compare everything with the cookie box. And he actually used the tiny ML approaches to put this on microcontrollers. And it turns out that putting them on, first of all, it's very difficult. The tools aren't quite ready yet. Same problem that we are encountering with HLS4ML. These tools are under development. And so we keep encountering all the bugs that are, the test case. So he worked very hard to get those running. He did, but they are very good for power, but very bad for latency, right? So the latency does not compare to FPGA, but the power is slightly less.
No, because when you compare with the FPGA, it's another league, no?
Yeah.
Okay,
but if you have a very low power application, all right, you need something that's very low power and you don't have any latency worries. If it takes a second or two, that's fine. Then tiny ML with a microcontroller will be easier to use than an FPGA.
Wonderful. Second check. I wanted also to say it aloud because I am seducing Alexander to enter in this field in his PhD. And he's there. I want to ask you. Thanks a lot.
You're very welcome.
Any more questions? You can write in the chat in Spanish if you like. We can try to translate. Yes, Jorge, please.
Hi, thank you a lot for your presentation. I have one question in terms of the model. So what process should be used to avoid introducing, or how we can identify bias in the different models that we train?
Okay, so how do you avoid bias in the models that you train? So that depends on the data set. And the first part of the question I missed. Can you repeat the first part?
How we can identify bias, or how we can avoid introducing bias in the models?
Okay. So it's almost impossible to have absolutely no bias in the model. So the idea is to recognize what biases is present in the model to make sure that you circumspect, so that you tell people this model is good for this type of data and only this type of data. And so the bias that you want to make sure is basically what is the use case, and to think about all of the things that can happen in that use case. I don't know your background, but in engineering, we have a similar thing in the risk assessment, right? So you want to make sure that all the risks are accounted for. In the same type of thing in your data set, you want to take into account all the biases that you want to watch out for. The example that is easier to understand is when you make a data set on a group of people. Well, is your group of people representative of the population that is going to be used in the application, right? So if you are trying to make an application for the people of Quebec, and if you are trying to make an application for the people of Ecuador, you will not have the same biases in the population. And these were both gender, racial, cultural profile, all of these things will be different. So depending on what your application is for, will those biases have an impact? Now, if you go to particle physics, then you can end up with a simulation data set that somebody created that is focused on hadron collisions, right? So you only have hadron collisions, but the application that you're aiming for will actually also have electron collisions or electron things or photons, right? So you have to make sure that these two things match and that these things match in the same ratios. And that is difficult. That's why it's in the challenges. So there is no automatic way of checking this. It's just something that you have to manually verify. And I don't mean verify inside the data set, but what am I going to use this for? And is it representative of the population it targets in the end, whether that population is humans or particles or anything else? Does that help clarify a little bit?
Yeah, basically I work with particles.
Yeah.
I made a model and my model worked really good when simulate data, but when I start using in the real data, I have some troubles. So I
Yes.
think it's about bias.
Okay. So
I
in
want to
this
check it.
case, there might be a bias in both of them. So you can verify if the ratios of the types of particles, the ratios of the interactions are pretty similar if you're missing something. But one of the things you can do is once you've trained on your simulated data and you're satisfied with the performance, you retrain on real data. So you make yourself a real data set. You're going to label that data set with real data and you retrain your model. That means you're going to need a smaller data set than you needed initially because you're starting from somewhere that's near where you want to go. And you're going to get closer to a high performance on the real data. So that's what I would recommend at this stage.
Okay, thank you. Something like transfer learning. Yeah, thank you.
Yep.
Oh, thank you very much. There is another question for Audrey. If not, I would like to thank you again. Oh, okay. Yeah. No. Teófilo, you want to ask a question or?
Oh, I
No,
think
not question.
it's
It
for
is
another
just
purpose.
another topic.
Okay.
Thank you.
Sorry. So, okay. So again, thank you very much, Audrey, for your collaboration. Spectacular talk. We have a lot to learn about this field and these applications. So we hope to see you again and continue to talk about this matter that is very, very interesting.
Absolutely. Well, thank you again for the invitation. It was a pleasure to talk to you.
Thank you again. Thank you all and see you in